So if you remember from last time, well, not last time, I guess 2 times ago, but whatever, we were talking about backpropagation, and I was being really hand-wavy with it, saying like, oh, just trust that we can take this gradient. And people, I think, got a little bit annoyed at me. And I asked who wants to see the math behind it, thinking that like 2 people would raise their hands, and then more than half of the room raised their hands. So today we're going to be going over the actual math behind backpropagation. And I'm going to try and do it in an intuitive way. The only annoying thing is, right now, like who of you have taken up to Calculus 2? Hopefully most, if not everyone. I see most people, and if you don't have your hand up, you might just have not been listening to me, hopefully. And then who then has taken multivariate, so Calculus 3? Okay, so this is pretty good. The main thing we're going to see that's different is you would typically see like your full f of x is equal to this equation, or f of x and y is equal to this equation, and then you would derive with respect to one variable. We're going to do the same thing, but when we do the chain rule, which is like the most important thing, and I'll justify that soon, you tend to start with the very end of the equation and then build back up towards the front instead of from the front to the back. So I think that doesn't make too much sense intuitively right now, but hopefully when we write it out on the board, it'll make more sense. And then I'll also try and justify why that is. It's for computing reasons. It makes things faster. But for now, I wanted to skim over the backpropagation slides we had, and then hopefully we can take that and try and make a simple neural network on the board, and then we're going to manually trace through it with our derivatives. So I guess before we get started, does anyone have any preliminary questions to get out of the way, or if there's anything from the past few meetings that we've been missing? You have a question?
3 blue, 1 brown.
He does. So 3 blue, 1 brown has 2 videos on backpropagation. One of them is like the very intuitive, what is it? And then the other one is I wouldn't say a deep dive, but it uses the actual mathematical language to explain how to do backpropagation. I have 3 videos that I've put into the Discord that hopefully everyone will watch, but realistically, no. But the third one is a 2-hour-long video about creating your own backpropagation engine, which I might show up on here depending on time. But that one is a really good one, and I'll try and get you all to do that later. Okay, any other questions before we try and skim through this stuff? Sweet. So you'll see I did not plan out slides at all, so I'm going to jump around these. So if you remember, we previously talked about learning and how we have our neural networks that we've built out, and we've gotten some output, and we want to compare the outputs to get our cost function, right? So we want to minimize our cost function. And the way we minimize our cost function is by doing gradient descent, right? So if you've been here for the past few meetings, that would hopefully make sense to you. We're going to dive into gradient descent today. And importantly, we test on a bunch of examples, which I will hopefully also get to show today. And then once we start with our utter trash neural network, our completely random one, we will see the math on how we can take the derivative and then slowly train our network to like move towards these ideal results. So this was meant to be like the really surface level. Here's the reminder of backpropagation. Here's some math. That's great. Hoping that the board will turn off. I'll clear this. Go back. Sweet. Okay. So previously, we've looked at a perceptron, right? We've looked at this structure where I showed like there's the 2 halves of your perceptron. You have your summation side, and then you have your like output, and this is your activation function. And typically, we would see a number of inputs going in that we sum up along these weighted sums. right? So these connections coming from our previous like layer or maybe our input layer have weights to them, and then we send them out with its own special weight, but we won't worry too much about that value. But then the input values ended up being, say x1, x2, because we can grab values from previous neurons and then feed them in. So if we looked at just the equation for this neuron that's relatively simple, it wouldn't be too bad. It would just be our like x1, w1, so x1 times w1 plus x2 times w2. But importantly, and something that I usually don't show on this diagram, there's also the bias that's just kind of implicitly in here. So we also have our bias term. And this is our whole like summation side. So you'll see me use S when we draw a different diagram later, but we want to sum up all of our terms in the first half, and then we want to squash them. We want to use an activation function so we can get the nonlinear side of this. So because I've prepared this in advance, I don't want to derive anything other than tanh h today. So we can say that our output of our neuron, which I'll just say is O, so maybe we can say that this is our O value, is going to be tanh h of our sum. So this is hopefully like the very review side of things. I don't want to lose anyone here yet. So just at this, does this structure make sense to people? Have I lost anyone? You have a question?
Well, what's the plus B part?
Plus B. So B is our bias. There's two different ways to think about bias. You can say that there's either like an implicit bias term in our node. It's just another parameter that we can train on. Or you can say that there's another node that's like a constant 1 and it's connected, and then the weight of that connection is the bias. That's either way of thinking about it is fine. Have a question?
You said if there was a name. What's the name of the whole structure?
What's the name of the whole structure? This is like one neuron. Perceptron is the most common name, I think. You can think of it as node. It's just node in the graph.
So is there a bunch of them, or is it all feeding to one?
Are there a bunch of them? This is really good. We are only going to look at one perceptron today because I do not hate myself. When we do the math, we are going to do backpropagation across one perceptron. And then hopefully I'll also add a little bit more here to do a loss function on that one perceptron. In reality, you would have maybe 100 of these in a layer, and then you'd have maybe 100 layers. Maybe not 100 layers, but yeah, this is just one single perceptron. Maybe there's another one here, and it keeps going.
Would they be like parallel kind of?
They'd be parallel.
Or like would they all feed into each other?
I think you're asking me if like there's layers. So if we look at a very typical neural network structure, you might have input layers over here, you might have output layers over here, but in just one dense layer, this is called, you tend to have something that looks like this, where you have fully connected in just one layer. But these nodes are not going to be connected to anything over here, and these nodes are not going to be connected to anything over here. There's just locally one layer. All right, anything else? Question?
What's like the output again? Like how does that?
Output?
Yeah.
So output is the resulting, like after we've done our summation and then after we've activated it. So output is going to be fed into the next layer of neurons. So if we've done our summation and activation in this, this little neuron, all of that output value is going to flow through each of these connections. And that's what's then used as the X1 in the next perceptron. These are good questions. Any other questions? All right, so when we want to do our training, like what is our ultimate goal?
Make our cost functions close to 0.
Yeah, to minimize our cost function. That's perfect. So how conceptually, I think, so most of you have taken calculus. Conceptually, how do you do this? And although, yeah, go ahead.
I like the local minimums.
Yeah, find the local minimum of the derivatives. This is good. You take the derivative, right? Okay, so what do we want to take the derivative of? Like just just take a moment to think about that. What are we trying to derive? What do we care about? Okay, so you're taking the derivative of the cost function with respect to what? You have an idea? Parameters. Yeah. So when in this equation, we have the tan h of all of this summed, right? One way we could try and do gradient descent, like the very human way, is to try and take the partial derivative of the output with respect to some parameter. So let's just say W1 is one of our parameters, right? So we could take the derivative of the output with respect to W1, which is, I'm not going to do this whole thing right now, but the rough idea is that you want to take the whole derivative of, I'll just say S for now, right? S is our summation term. And this will be equal to some value, and that'll be your gradient for the W1 term. So then when you have that gradient, you can sort of, you take the negative of that gradient to go down the slope, right? So the issue here is we need to do this for W1, but then we also need to do this for W2, and then we also need to do it for B. And this simple single perceptron example, that's not so bad. But imagine for just a moment you had 100 nodes in your network, or sorry, 100 nodes in one layer, and then you had multiple layers. Think about how complicated it would be to have the final output, right? Imagine we had one final output node. And imagine how complicated it would be to take the derivative of this output with respect to this weight all the way over here, right? It's possible, but you're going to have nested tan h's inside of each other. You're going to have all these summations to deal with. And it becomes very annoying and computationally expensive. So this human way of thinking of the derivative is maybe a little bit rough. So we need to think of some slightly more useful way of doing this. And machine learning people, they looked at this for a while, and they realized that the issue is the chain rule, right? Since we have all of these nested layers inside of each other, you have to be able to take the chain rule hundreds of times if you have a deep enough network. And that is really frustrating. So they found a way to, instead of having to take the chain rule 100 times if you have 100 parameters, you can instead work backwards from the front, or sorry, from the end of your network and just backpropagate, we said the name, through the entire network. So we want to try that now. And I only have so much space, so I'm gonna erase this structure. And we are going to draw out a slightly different diagram. And this is going to take me a moment, so please bear with me. So one way to think about this is decomposing your complicated O function into every single individual term. And this is the part where you guys will hate me, so bear with me here. We have our x1 term. We have our w1 term. These are both in their own boxes. We're going to draw it like this. And notably, every single box I'm going to draw here has two terms in it. It has a value and a gradient to value. So the value, for example, is going to be just whatever we put into the input layer, or maybe whatever the output is of that node. And then we're going to feed that into the next layer, right? And then the gradient is just what's going to come back when we do our backpropagation. So each value here, each box stores two, the value and the gradient. I said a lot of things. Have I lost anyone? Have a question? The box bit. The box bit stores 3 bits of information. What variable it is. It stores the value, and I'm going to plug in some example values soon. For now, it's just going to be empty. And then the gradient, which we are going to fill in using calculus later. Have I lost anyone? Any questions? OK, so this structure is very common when we do backpropagation. When we do our equation, and I don't mean to baby you, but I'm going to make you say this to me. What are we doing with x1 and w1? Someone just say it. Multiply. Right, so at this step, we have our multiplication step. And this outputs some value. I'm just going to call it x1, w1. And this, once again, carries 3 values in it. We'll fill those in a moment. Let's do the same exact thing over here. We have our x2. We have our w2. It has its 3 values, of course. And then, once again, we're just going to multiply them. OK, so this outputs x2, w2, which, again, has values. So we don't need to worry about those yet. And then I'm going to add another new parameter here, the bias one, right? Because our summation term has this bias term. So I'm going to add this bias, which, again, has 3 values. All right, and then what should we do next? I'm not trying to baby here, just trying to get engagement. Someone say something. We add everything. So if we have an adder node, we can do this. And this will output our S term, right? Because that's why I named it S. I didn't want to have to draw out the whole thing. And this, again, has our 2 terms. And I'm sort of running out of space on this right side. So I'm going to draw this slightly differently. Actually, you know what? This is fine. So if I then have one more operation, and this one will be called tanh, right, our activation function, this will then output our O value. Which is not a very simple operation, but it's there. OK, so this diagram, this whole thing, is effectively the same exact diagram as this simple perceptron diagram. And hopefully we all see that. If not, could you please ask me a question now? Yeah, so all I've done is taking this perceptron diagram and expanded out into the most annoying and long possible system. So I'm going to pick some input values, and then we're going to do our forward pass over our network, and then we're going to do a backwards pass. So I have some highly contrived numbers here to make numbers easier later. And you know what? I'm going to use a different color. That will sound. All right, so these numbers, you can imagine that these, we'll say green is our numbers that we just put into the network for the feed forward pass. So that means it's like your training data going in. This isn't like a mathematically chosen thing. It's just what your data set looks like. So for example, we have these. And I think we had 0 and 1, the other one for contrived. Again, these are just contrived numbers from a training set. You know, it will look differently depending on what neural network you're working on. So you know, I'm not gonna. I'm gonna baby you again. What's the value here? Someone just say it.
1 is 6.
Yeah. Right. So I know I'm babying you a little bit, but 2 times -3 is -6. I forgot to input this bias node. This one is highly contrived. Just trust me. This is 6.8814. Don't worry about it. And what's this bottom term here? 0, yeah, because one times 0 is 0. All right, we haven't lost anyone, right? Keeping it simple. We love our forward pass. Our forward pass is nice and easy. And then our term here is a little bit annoying, but someone can say it, I'm sure. What's our value here in S?
0.8814.
Yeah. So we get 0.8814. Because all we're doing is adding up all of these values. And I think I do have it written down here, but if anyone would like to check my work, that would be great, because the tanh of this number is still going to be a pretty ugly number. In this case, it is 0.7071. I did choose the bias number for a reason. It'll be important later. OK. So all we've done right now is done all of the computations for one perceptron going forward. Right? We've kind of predicted what the output of our perceptron will be. Have I lost anyone? Any questions at all? Confusions? How this connects to anything? Go ahead.
Yeah, for like the outputs, like why do we even have like the tanh, or like is that just like a random function you could always choose, or like
Why do we have a tanh? So this is tanh is our activation function. Do you remember how I've talked about previously how you need to have it be non-linear? Tanh is just some arbitrarily chosen by me activation function that's not linear. In here, you could throw in sigmoid, you could throw in relu. I've only done the work for tanh, and I don't really want to do the work for the others. You are free to do that on your own. But this is commonly called like a squasher because it ends up looking like this function when you plot it. This is really poorly drawn, but it just squashes the value to -1, +1. Go ahead.
If you use like a much simpler function,
Yes. Yes.
like what's the requirement?
It has to be nonlinear. That's it.
Like x squared?
Yeah, x squared could probably output values that would be useful to train on. X squared in particular, though, is probably not going to be a good one. It'll probably still learn. It might just be harder to train on your data set. We've sort of developed a bunch of activation functions because like tanh, for example, you'll see everywhere in machine learning. Sigmoid, same thing. Relu, same thing. And then there's way more complicated functions. Like relu has probably 10 variations on top of it. So we've kind of chosen these functions because they're pretty good at specific tasks. In this case, I'm just using tanh for an example. Have a question?
Stupid, but when using like x squared as the activation function, like do lead to like exploding gradients or like problems like that?
Yeah, there's two main issues with activation functions. Like this is called a vanishing gradient when it becomes really close to 0, right? The slope is 0. And on the inverse side, you can get an exploding gradient when the gradients become so extreme. You get like numerical stability issues, that kind of thing. Yeah, both of those issues are pretty famous and are somewhat hard to solve. But you sort of choose your activation function to hopefully avoid those. It depends. Any other questions? All of these were really good questions. Okay, so yo, Denali, how you doing? All right, so now we want to go through backwards now, right? And just, I don't want to baby, okay, I said I don't want to baby you. I do want to baby you in this case. What is our goal again? What were we trying to do at the very start? Like what are we trying to do with this like parameters? Someone say it or someone, did I say again? Derivative. We're trying to take the derivative with respect, or sorry, we're trying to take the derivative of our output values with respect to our input parameters. It's like W and B. How do we do this? Does anyone want to take a stab at it before I try? Not that I'm going to make you write it on the board, but so the idea of backpropagation is that we can start with an extremely simple derivative right here, and then just flow all the way back through our perceptron. So right here, what is this derivative term? Does anyone want to just take a guess? Like what we're deriving what with respect to what in this case?
O with respect to s?
O with respect to s. That would be the derivative here actually, which I will just write down. So we want to take the derivative of O with respect to s, right? So for every little change in s, how does that affect O? Which is exactly what we want here. What do we want here?
The derivative of O with respect to the tanh function?
With respect to the tanh function. I'm thinking that that's the same thing with respect to tanh of s. What, you have an idea?
Well, how about derivative of tanh with respect to x?
The derivative of tanh with respect to s. I'm thinking that's still the same thing. You have an idea?
Derivative of our loss with respect to O?
Derivative of loss. You are like 4 steps ahead of me. I won't say that you're wrong because that's a good idea in the future, but not right now. I wanted to say this and annoy you all with it because it's actually so easy, and you'll be annoyed that we want to take the derivative of O with respect to O, and what does that equal?
1.
None. Crazy. So in this value, we'll say orange is our gradients. We start with the most basic value, right? And this intuitively, hopefully makes sense. Does anyone want to like try and explain the intuition of what this derivative means? Anyone take a stab at it? There's no wrong answers here because it's like the intuition. You have an idea?
It's just a change of O with respect to change of O.
Yeah, I mean, for every change of O, how much does that affect O? And this is like linear, right? It would be 1. If we had like a multiplier in here, like 2, it might be 2 instead. But since it's just itself, we're at 1. Okay. This part, though, is a little bit harder. I have a few things written on the board over there. There are 2 ways we can do this. I can either derive the derivative for tan h in front of you, or we can go to Wikipedia and look it up. Which one do we want? We'll do a vote. Who wants me to derive it? I hate you all. Okay. I took notes on this for a reason. Okay, so we want to take the derivative. It was just right there. Why did I erase it? We want to take this derivative. So let's choose a new color. We need more colors. You have a question?
You like give a very brief background on like what tanh is kind of like what we're doing.
Tan h, so I drew it poorly up here. I'll try it again. Tan h is just a function, right? On this graph, for example, that when you take an input, it like squashes it between -1 and +1. So it sort of approaches -1 on this end, and then it does this like flip, and then it keeps going.
Isn't that just the inverse of tan?
Not quite. It's a little bit different. This is tan h. I would show you in Desmos. I'm not bringing the board down right now. We could, if you remember later, I'll bring it down.
I think we need to squish them, like between +1 and -1.
Why do we need to squish our values? This is just an activation function that I've chosen. You could choose any activation function. These like squishing ones, like sigmoid and tan h, are very common. It would be hard for me to justify it because it's really hard to justify why squishing it is good. You can think of it in terms of a neuron is either like off or on. So like it's not perfect, but in your own brain, your neuron will like fire, turn on, and then like turn off. And then you can imagine that neuron turning on turns on another neuron. So instead of having some value like 0 to 1 million, you have this like really compressed like -1 to 1, so it's either off or on. That's sort of the rough justification. There's better ways to mathematically say that, but tan h is just this, I say simple, it's this weird function here that squishes. If you want to explore that further, that's something you kind of just have to test. Like, why does it work this way? Why do things work when it's not linear or when it is linear? So this is something to just test on your own.
Note that intrigue tan x, like just tan x, is equal to sine by cos. So I'm assuming tan h would something be sine h by cos h.
That is a really good start. I was actually going to ask that. So tan h is sine h over cosine h. And then we're going to have to take the derivative of this. Before I get started, though, any other questions? You have a question? It shouldn't be too bad. I had it in like 2 or 3 lines in my notes. Maybe I'll just copy my notes so we don't take too long. Okay, so derivative of this. We want to take the derivative with respect to x of tan h x. And this means we have to do the quotient rule because we have sine h over cosine h, or whatever. So in the division rule in derivatives, you start out with your f prime of x.
Derivative of cos h.
Derivative of,
So derivative of sine h first.
yes.
Cos h.
Yeah, and the important thing here is we're using these functions. So one way we can rewrite this tan h is
E to the power of x plus e to the negative x divided by.
it's going to be a minus instead of a plus. And then we have our,
Oh, but isn't it flipping over though? Because it's being divided by 2.
yeah, so these two twos will cancel out.
Mhm.
And then we have the sign up top, right, which is the minus, and then the cosine at the bottom, which is the plus. All right, have I lost anyone? Okay, so taking the derivative of this, we start with derivative of top times bottom. So this will be e to the x plus e to the negative x times the bottom. And you'll notice a pattern really quickly here. You said it. These two are the same thing, which will make this derivative really nice soon. We just have to keep going through it. In the quotient rule in derivatives, you have to subtract then your next term, which is your f of x term, e to the x minus e to the negative x. And I did not give myself enough space, I guess.
Negative e to the negative x.
Exactly. It ends up being the same exact term. And they match up, which is perfect. And then
X plus e to the negative x whole squared.
they square them. Yeah. Let me just double check with my notes because it'd be kind of embarrassing to mess up here. All right, sweet. Who wants to simplify this? How do we simplify it? I'll get you started. Okay, so you can first combine our like terms. I say combine like terms, but it's not really. We're just, we can rewrite this in, as squared. And then we can combine our other terms. And all of this is still over e to the x, because we haven't simplified this at all. And hopefully now this will be a little bit more obvious what we can do. Someone say it. It's not too bad at this point, right?
Isn't it just a plus b minus b?
A plus b minus.
Like, we assume the denominator in the form a squared minus b squared, and then we just expand and write.
Yeah, these terms kind of like cancel out. And then you have this. So we want to have 1 minus this e to the x. And all that is squared, again, over the same denominator. All right, have I lost anyone here yet? Okay, what do we do with this? We can simplify it really nicely.
Square the
Square the whole thing. I suppose yes. That's one way to think about it. I don't know if it gets us much further. Does anyone have any other approaches?
take the negative outside.
Take the negative outside.
Oh no, that doesn't make a difference.
Yeah, I don't know if we can take a negative. Do you have an idea?
Factoring or something?
Factoring.
A minus b, a plus b or something.
We could try that. I suspect it won't help us. We could probably, it's still correct, but a hint will be to look at these. Can anyone take a guess at what we can do? I'm only trying to make you all do this because you can derive your own.
Did you just say the top is sinh squared, well, 2 sinh squared, and then over 2 cosh squared?
Yeah, and then the 2's cancel out again, right? And I'm going to do one more step for you. 1 minus tan h squared of x. Does anyone disagree with me? So the reason why I'm taking so long and trying to make you do it is because this is building a backpropagation engine. Every single operation, like tan h, but also like times and plus, they sort of have their own derivatives. And if you can make the derivative for every single operation, you can make your own backpropagation engine. And maybe it won't be as fast as PyTorch, but conceptually speaking, this is really cool because you can train your own neural networks from scratch using the highly efficient calculus methods, using the same methods that are used in modern architectures today, like PyTorch. So That's why I prepared this stuff for tanh, because it's not too bad. And now I have the value, but I want you guys to do it on your, if you have a calculator or on your phone or whatever. If we now have our derivative here, what value or what happens here? Let's try and connect our dots. I'm going to see if I can get you guys to get there on your own without me saying it. So you have an idea?
Subtract 0.071 whole squared from 1.
Don't we? From 1.
1 minus 0.071 whole squared.
So this minus this.
1 minus 0.7071 squared.
Oh, sort of. So this derivative, let's start there. If I get back to my orange, which I threw on the ground. What is this derivative? We just took most of it. What would you say that this derivative is equal to? That's half of it. What's the other half? Tan h squared of x. And we have to multiply by something. What do we do? Yeah, which is technically the same thing. But importantly, our gradients pass through. And we have to keep doing that. This is what backpropagation does. All right, so I'm going to save the effort. And I'm going to say we chose a really, really clever bias term where this ended up being 0.5. All we do then is put this to 0.5. Now this technically isn't precise enough. It'll be like 0.4999, but deal with it. All right, so now we have this step. We took our output, and we have now the gradient of our summation. Intuitively now, what does this gradient mean? Who has an idea? Train of thought. Wrong answers are good too.
We're changing that solution.
Yeah, for every, all we've done here is we're measuring the change in O for every change of S, and it has this much influence. Maybe 0.5 is considered a lot of influence. Maybe it's not too much. It depends. And now, is this useful? Or maybe, I guess I'll say is useful in a roundabout way, because we eventually have to use this. But is this useful now? Probably not, because like what was our goal, right? We have our cost function that takes in all of our parameters, and we want to measure the gradient of that cost function. So S, is this a parameter? No, S is not a parameter, right? S is just some intermediary results in our neural network. We care about W1, W2, and B, our parameters. So we have to keep going. We have to keep going backwards. So next, let's just look at this B term for a moment. And I'm going to come down here. We want to look for the derivative of the output, right? For every change in the output with respect to our B term. So every little change in B, how does O change?
So change in O by change in O times change in O by.
Change in, I think you are.
Or change in S by change in O, and then times change in.
Change. That looks more like a 2. So our change of O, you're right, change of O over the change in S. So for every change in S, how does that change O? And that's going to be times.
Change in S times.
Change in S.
B.
We're just going to say the derivative of B of this function here. So we can say x1 w1 plus x2 w2 plus B. Does anyone disagree with me here? All right, so
The DS get canceled out.
wouldn't the ds get canceled out? You can write notation in that way. I've seen it written that way. I think, you've watched a backpropagation video too before?
Yeah.
There's another way of writing it where it does like cancel out, sort of. I'm not writing it that way because I find it to be less intuitive. There's like 100 ways to write this. So intuitively, what does this equation mean? What is it doing? Anyone here? Anyone is good. There's like very little judgment here. Can anyone recognize why we have this term? You can just give an explanation. You can say the math reason why we have this term. Well, what's going on here? You have an idea?
It's a partial derivative.
Partial derivative, you're right. But I guess a better question for me to ask is, why, when I took the derivative of the output with respect to b, do I have this term in here? Like, why am I not just doing this right here? Yeah? Yeah, we're going back in circles here. Chain rule. A chain rule is exactly that. So remember when I showed you, I guess I erased it by now, the original equation where I tried to derive with respect to d1, or sorry, w1, and I didn't actually do that whole derivative because it was complicated, because we need to do the chain rule over and over again. But this time, we've already sort of done the chain rule, right? We've done it from the back. And now we're feeding it forward. OK, so this is equal to what? What's this DODS?
The 0.5.
0.5, right. And then what can we simplify this term to? This derivative of the s?
W1 plus x2 W2.
In a partial derivative, that wouldn't be necessarily true, because we're deriving with respect to b here.
B is not present in the first two terms.
Exactly.
So don't we treat them as constants?
Don't we treat them as yeah, exactly. We treat them as constants, right? So x1, w1 is a constant. So
Would be 0, then it would be 1.
yeah, so this simplifies to 0, right? Because this is a constant, plus another 0, because this is a constant. And what's the what, plus 1? Exactly. Because the derivative of b with respect to b is 1. OK. And at the end of the day, our gradient just became 0.5. Kind of anticlimactic, right? This is a thing that machine learning people love to point out, and I wrote down a couple of terms here. They love to call these gradient distributors. So this plus term, does anyone want to take a guess what this here, we've calculated this gradient, 0.5. What's this term?
0.
0. Why is it 0?
Because you're basically doing the derivative of O with respect to B, but there is no B, so you're just treating it as a constant.
This
Yeah.
is actually the partial derivative of O with respect to this like x2 w2 term. Yeah. So this, if we take with respect to x2 w2, the same thing happens. This goes to 0. This goes to 1, right? Because we're taking with respect to x2 w2. And then this b is constant, right? Goes to 0. Have I lost anyone? Question?
2, 0.
Isn't x2 0? It is. This will become important later. But this x2 w2 term,
Oh, the whole term. Okay.
you can think of it, don't think of it as like the value right now. It's a variable. And then the value will come in important later when we actually evaluate gradients down the line. And you'll see that. Any other? Go ahead.
Forget how the O by D x2 W2 is 0.5. This one right away.
Sorry, you don't get how we got 0.5? OK, so I'm not going to write it out, but just assume that instead of b here, I have the x2 w2.
Yeah.
What is this term in that case?
This is just 0.5.
Exactly. And then when we do this derivative with respect to x2 w2, what is this term?
That's 0.
Right, because it's a constant. What does this term go to? Exactly. 0. So you get 1 times 0.5, same thing. All right, any other?
Just a question.
Yeah.
Would it be negative?
Can it be negative? If your gradient here was negative, it's going to just pass through. It's going to be negative. If this is a different operation, like a subtraction, it'll be negative and positive. That's just something you can derive on your own. I'm trying to keep it relatively simple today, but any other?
Will they always be the same as S then? Like,
Yeah.
like, I mean, like, is it just like this in case it happened to be like that, or is it just like always like that because of like just the way the equation is set up?
The addition operation here is crucial. It's called a gradient distributor by the machine learning people, those nerds. It's because the gradients from the output, like for each input, it's just the gradient of the output. So this gradient just flows into each input individually. I know some machine learning people like to call it like a democratic flow. I hate that. It makes no sense to me. But you can think of it in many different ways. It just flows backwards with no change. Go ahead.
Just to clarify, like if you have like a plus like operator, then like all the input gradient output.
Exactly. If you have an addition operation, right? If you have any addition node, if you want to think of it in terms of graphs, then all of the gradients are just going to take on the same value as the parent or output node.
What about the boxes behind the multiplication?
Yeah, we haven't done that yet.
Right, because it's not addition. It's
Yep. When we do these boxes, it will look a little bit different. So we'll do that next. But before I move on, this is, I suppose I mean to say that this is probably one of the easier examples because the derivatives end up being really nice. So I don't want to lose anyone here. Do I still have everyone? Any questions at all? Any confusions? Okay. So I have once again run out of space. So I'm going, where did I put my towel? Whatever. Here we go. So now that we have our gradients at this layer of our perceptron, we have to keep going and do our previous layer. And hopefully now we've kind of done this enough that you have the tools to do this. So I'm gonna work in black this time. Why not? So let's look at this W2 term for now. So we want to find the partial derivative of what? Just trying to baby you all into this because it's like important-ish. We're taking the partial derivative of O, right? Because we care about the changes in the output
W2.
with respect to W2. Exactly. And for W2, what's that going to be?
Changing X.
Exactly. So we care about the change in X2 W2, right? So this change.
Is
Exactly.
derivative of S.
That's sort of encapsulated here. That notation, again, is valid, but I'm just going to say that that's contained in this. Instead, we care about the derivative with respect to W2. And in this case, what's our equation? Like what goes in here in the derivative? X2W.